And we should be, let's go live on TikTok. We are live on YouTube. Let's pop out our chat so that we can get that going. We are live on YouTube. We will be live on TikTok in just a moment. Welcome, welcome. Howdy, everybody. We're just getting started, so if you're just joining us, nobody's here yet. Who am I talking to? Nobody. Hello, welcome, welcome. We have just started for the day, so we're going to give it a little bit of time for people to stroll on in. Meanwhile, I'll, be talking to the chat. People can stroll all in. Oh, I should send an announcement to the Discord. That's what I should do. Howdy, howdy. Hope everything's going well for everybody who's just now wandering on in. We'll be getting started in just a bit. Are you live on TikTok yet? Yes, I'm live. Oh, let me make sure that my audio is clear. Audio on TikTok is always good. Audio on YouTube also seems like it's probably good. Oh, the name of the TikTok or the live is probably wrong. Howdy, howdy. Oh, I should change the name of the live to have the name of the paper in it. Edit video. And I should also have the name of the author in the description. Live streamed on March 25th, 2025. By Robert Brandenberger. There we go. Howdy, howdy. We're just waiting for people to stroll on in. We'll be starting in just a minute. And while we're starting, I may as well, take care of some things. Howdyology indeed. Indeed howdyology. Can you review my match homework? No, I cannot, unfortunately. It's actually illegal, turns out. Yeah, we will also be reviewing the newest plantology papers. This is very important work that has to be done. Plantology is a serious science done by serious scientists. What you up to? Well, we're going to be starting a peer review in just a few minutes. Just letting some people stream in. Is this a real peer review or just reviewing already published? So these are not published. These are the papers that, so I can't publicly do an actual peer review that I was contacted to do by a journal, because that has to be anonymous, and if I did that live, it wouldn't be anonymous. However, what I am reviewing is a new paper that is not yet peer-reviewed. So we're going to be looking at a paper that just showed up on the preprint archive, and we're going to be talking about it. Mostly, I'm not going to be critically evaluating it. I might catch some typos here and there. But mostly what we're going to be doing is just talking about the ideas that are present, because they're interesting ideas, right? And it's a good way to encourage me to actually read more papers. How do I begin to comprehend this stuff? You just read it. The more you read, the more you understand, right? That's how we learn. At least that's one way to learn. All right, we will be starting again in just a minute. Just want to see those numbers go up to about 100 people, and then we can get started. And we should be good to go soonish. And make sure that everything's good. Oh. Okay, I think we're good to go. Right, y'all. So let us get started by just providing some context here. So the paper is called Why the DESI Results Should Not Be a Surprise. Now, the context here is that there were new DESI results that came out. Now, let me explain what those are, just so then everybody knows what I'm talking about. DESI is the dark energy spectroscopic instrument. It's a telescope that is, or it's a device really kind of attached to a telescope that's in Arizona. I made a video about this recently. It was posted on both YouTube and TikTok, but essentially what this telescope does is it has a whole bunch of robotically controlled fiber optic cables that then are attached to the telescope and can be used to basically study the light spectrum from a whole bunch of different galaxies all at the same time. And so they did this to study the light spectrum, which gives you a lot of information about the galaxy, for 15 million galaxies over the last few years. And the goal of this project is to basically get a very accurate map of the large-scale structure of the universe in the more recent universe. So these are not super, super distant galaxies. These are like, a little bit closer than, what JWST might be seeing. But the reason why they're doing this is because if they can figure out the average distance between galaxies at given distances, so let's say a galaxy is a billion light years away, say, well, they might want to know how far away galaxies are from each other a billion light years away, because that would tell us about how far away the galaxies were from each other a billion years ago. So if you can get a very accurate map of the universe this way, about where galaxies are and what color they are, which will tell you about how far away they are, then you can actually start putting together a picture of the average distances between galaxies as a function of time. And that information further informs on how the universe has expanded, because the average distance between galaxies essentially depends on initial fluctuations in the very, very early universe. And so this is a way to measure the dark energy in the universe, the cause of the universe's accelerated expansion. That's why it's called the dark energy spectroscopic instrument. It measures dark energy. It uses spectroscopy. This is kind of examining the light from an individual galaxy to do it. So the big news that was announced last week is that they found that, at least with their data in combination with other more recent, with other data from other experiments like the Planck telescope or like the Pantheon plus supernova data, they found that the dark energy that best fits their data is actually not a cosmological constant, which is what used to be thought was the cause of dark energy. Dark energy is that thing responsible for the universe's accelerated expansion. And it was believed, simply for Occam's razor reasons and that it fit the data really well, that if there's just a number that tells you how fast, or that controls how fast the universe is expanding, a constant that's the same everywhere throughout all of time, that would give a pretty good fit to the data that we had up until recently. And that was called a cosmological constant. And the name of the standard model of cosmology even gets its name from the cosmological constant. The name of this standard model is called lambda CDM. The lambda is the symbol that's used to represent the cosmological constant. And the CDM is cold dark matter. That's the other piece of the standard model. Anyway, the point is that the DESI results found that actually it's a better fit to the data that they have if the cosmological constant isn't constant. Moreover, that is to say, if dark energy is not well described by a cosmological constant, but rather it's more well described by a dynamical dark energy, whatever it might be. So that's the context of this paper, that there is this huge breakthrough, this kind of surprise data set that was released about a week ago by DESI, surprising everybody, namely that the cosmological constant is no longer, statistically favored, and that there is some alternative model that we should be preferring. So the title of this paper is Why the DESI Results Should Not Be a Surprise, because in a sense, they were very surprising. So this guy, Robert Brandenberger, out of McGill University in Montreal, is claiming that actually we shouldn't be surprised. So let's read the paper. It's quite short. It's only about 2 pages long plus citations. So we're not going to be here for long, but I think it's a useful paper, and it'll be have some very interesting things to say, I think. Just before we start, I'll answer some questions. Will this have any effect on the CDM part of Lambda CDM? It could. It depends on what future observations say. There's another question on YouTube. Has the data been verified? So this is 3 years of observational data, and this is the second data release that they did. The first data release presented this, which was using the first set of data. Their first set of data for the first year had this, basically they showed that this is indeed the case, that dark energy seems to be dynamical. And then after 2 more years of data gathering, in the third year of data gathering, it turns out that their data even more strongly favors the changing or the dynamical dark energy models. So it's still possible that there's a systematic error causing these, and that this is actually not a real thing, that it's, just a wisp in the data. But if I'm not a betting man, but if I did have to bet on this, I would bet that they're right. Anyway, let's read why it shouldn't be surprising that they're right. So the abstract is quite short. The recent DESI results provide increasing evidence that the density of dark energy is time dependent. That's what I mean by dynamical. I will recall why, from the point of view of fundamental theory, this result should not be surprising. Okay, fine. I don't know who this guy is, by the way, but he's in the physics university at McGill, and McGill's a good university, so I'm sure he's respectable. So let's just read. Hopefully this is a good size for everybody. I know that there's always issues with how big the text is, but hopefully it's big enough that everybody can see it. Let me center it a little bit better. There we go. Right. Sorry, there we go. DESI has just published from their data release 2. This is their second data release. The first one was last year when they released their first year of data, which combined with CMB data from Planck and ACT, CMB is the cosmic microwave background. So it's the light that fills the universe left over from the Big Bang, indicate a conflict at a level of greater than 3 sigma with the canonical lambda CDM model. So a level of greater than 3 sigma, what that means is that the probability is more than 99% likely that they're not wrong, that there's a less than 1% chance that it's a fluke. And so the point is that they have a conflict, their data is in conflict with the standard model, with this canonical lambda CDM model. This is the Greek letter lambda for those who don't know. Now, when testing the DESI baryon acoustic oscillations is the way that they measured the dark energy. They were measuring baryon acoustic oscillations when they were measuring the distance between galaxies. I made a video in depth on this. You can go watch if you're interested, but that's the context here. When testing the DESI baryon acoustic oscillation results in the context of a model which contains a parameterization of the dark energy equation of state W in terms of 2 parameters, W0 and WA, here's the parameterization, W of A, so this is saying that W changes when A changes. They're saying that W is equal to the original W0, plus some coefficient, WA, times 1 minus A, where here A is the cosmological scale factor of a spatially flat universe normalized to A equals 1 at the present time. And we recall that W is the ratio of pressure density to energy density. Then the equation of state W0 equals -1 and WA equals 0 of cosmological constant is ruled out at a level of greater than 3 sigma. Okay, there's a lot to unpack here, but let me explain what's going on. So when we talk about different types of matter or types of energy in the universe and the effect that they have on the expansion or the contraction of the universe, we talk about it in terms of the equation of state W. So the equation of state W is, in some sense, sorry, I just got to double check something. Yeah, the equation of state W is, it says here, it's the ratio of the pressure density to the energy density. So it's pressure divided by energy, right? And so, most matter has positive pressure and positive energy. In fact, all matter that we know has positive pressure and positive energy, or rather non-negative pressure and positive energy, which means that W would be 0, right? like think of dust kind of just floating in space. It doesn't have any pressure. It's not like exerting a pressure on anything. And so W would be 0 because the pressure is 0 and the energy is not 0. It's some positive number. However, you can have radiation, for example. Radiation, light, tends to push outwards. And so the example with the radiation would have a positive, a non-zero equation of state. Now, one of the strange features of our universe is that really, depending on what you fill our universe with, whether it's like what kind of matter you fill our universe with, in terms of the equation of state W, really tells you how the matter evolves. So if your equation of state is less than -1, meaning that the pressure is negative and the energy is positive, that actually causes space to expand at an accelerated rate. If it's exactly equal to -1, then that would be a cosmological constant. It will expand at an accelerated rate, but the acceleration rate will kind of peter off eventually, and it'll just be like a constant acceleration rather than an increasing acceleration. If the equation of state for whatever is filling your universe is greater than -1, meaning like -0.5 or something like that, then that means that it has that this energy, well, whatever's filling the universe, has a repulsive effect, but it's not particularly strong. It might not be accelerating. On the other hand, if you have a positive equation of state, that's sort of attracting. That does what gravity normally does, which is, it causes collapse. So think of it this way. Negative equation of state is repulsive. It's repulsive gravity. Positive equation of state is attractive gravity. And so that's what's going to drive the expansion or the contraction of the universe. Now, if there was no dark energy, everything in our universe would have positive or 0 equation of state, which would mean that the universe would expand, but then slow down and then recollapse. And this is what was thought for a long time, until Einstein introduced the cosmological constant into his equation to counteract this. Because he wanted a steady state universe. So he introduced this cosmological constant to exactly balance out the collapsing nature of the rest of the universe. Now, this was a blunder in the sense that it probably wasn't correct. He kind of just added it in on his own. It doesn't have, without like any good reason. But then it was discovered later in the 90s that actually our universe's acceleration or our universe's expansion is accelerating, which means that maybe Einstein was right and we should put the cosmological constant back in. So now we're back up to the present time. This is the equation of state model that they're trying to describe in the DESI data release. Now, if the universe was just well described by a cosmological constant and then matter and then light, like in the normal universe, then this equation would have a W naught here. That's a constant. It doesn't change. And then it would have 0 in front of the 1 minus A. A is the size of the universe. So if we say that the universe has size 1 now, it had size 0.5 sometime in the past, and it has size, say, 2 at some point in the future. So as A changes, this would mean that the equation of state changes. So if you wanted to model a cosmological constant, you would need WA to be 0, and you would need W0 to be -1. And that's what was being said here. That's the equation of state for a cosmological constant. W0 is -1, WA is 0. Now, what was found, and will they actually mention it? No. What was found is in the DESI paper, is that it seems to be that their data better fits a model where W naught is around -0.75 and WA is about 1.5, which means that as the universe gets bigger, this 1 minus A gets more and more negative. And as that gets more and more negative, if this WA is also negative, that will mean that WA would be about 1.5, W0 is about -0.75. That would mean that the equation of state of dark energy was less than -1 in the past, and it's about 1 now, or it's slightly more than 1 now, and it's slightly more than 1 now, and it will be even more than -1 in the future, which means that, at least according to the DESI data, the strength of dark energy is going from much stronger in the past to weaker in the future. Who knows what the future implies, what the future will actually happen, but that is the claim of DESI right now.
So that's the discussion here, that the cosmological constant has been ruled out at a level of greater than 3 sigma. And when we say it's been ruled out, what we mean is that their data is not compatible with W naught being -1 and WA being 0. That was one sentence. Let's keep reading. The data favors a time-dependent equation of state, with W naught being greater than -1 and WA being less than 0, which corresponds to a dark energy density which decreases as a function of time. Note that this result is obtained without making use of supernova data. That's not quite true. They did use supernova data, but they obtain it even without supernova data. This result is much stronger than the data from the initial DESI release, which showed some evidence for W naught greater than -1 and WA less than 0, but with lower significance and only when including supernova data. He dropped a period. In fact, the evidence cannot be seen when making use of different parameterizations of the dark energy equation of state, is a little footnote. Additional evidence for a time-dependent dark energy density can be obtained when adding the sum of neutrino masses as a free parameter to the data analysis. I didn't know that. What's this reference? Constraints on neutrino physics from DESI DR2 BAO and DR1 full shape. Let's go take a look at this really quick. Oh, this is quite recent. This is quite recent, actually. Oh, actually, this is the same data release. Yeah, this is the same data release. Let's go take a look at it really quick. So they're talking about neutrino masses, giving evidence for time-dependent dark energy density. So let's just scroll down and see if we can find something. Neutrino mass tension. Here we go. Profile likelihood. I just want some good old pictures. Okay, here we go. So here's lambda CDM. Okay. So here's lambda CDM, and I guess what's the claim here? Neutrino mass profile likelihood using DESI BAO with and without the CMB lensing information from Planck. The horizontal line indicates change in chi-squared of 3.84. So I guess the claim is that that you actually expect a sum of masses and neutrino masses to be about here, which is negative, which would be kind of strange. But here, I guess you expect it to be positive? Is that the claim here? Let's actually do a little bit of reading. Okay. First, consider combinations. No, I want to see what lambda CDM has to say. So we want to look at neutrino mass tension. Our baseline constraint on lambda CDM, on the sum of neutrino masses in lambda CDM, approaches but remains compatible with the lower limit from neutrino oscillations under the normal mass ordering. Okay, they gotta say something about lambda CDM for the sum of the masses. So they find that the sum of the masses from DESI is less than 0.053 electron volts, which is good because it's positive. We're not talking about the DESI results directly. We're actually talking about why they shouldn't be surprising. But I'm just looking for a reference because it was mentioned that in this paper, there should be a description of the sum over neutrino masses in the lambda CDM. Ah, here we go. Here we go. Okay. So, okay. So here we have lambda CDM, this plot here. With all of the data, this puts the sum of the masses of the neutrinos. Remember, neutrinos are particles. They have positive mass. The sum of the masses should be negative, according to the lambda CDM. But with the model provided by DESI, it's at least compatible. You know, there's some overlap with positive neutrino masses under this new model, WAWA. People are calling it WAWA CDM because it looks like WAWA. But anyway, so that's what's being referred to in this reference 6. So if you add the sum of neutrino masses as a free parameter to the data analysis, you get more evidence for a time-dependent dark energy. In the context of the canonical lambda CDM model, Bayesian evidence points to unphysical negative values for this mass sum, but when analyzed in the context of a time-dependent dark energy density described by the two parameters W0 and WA, the Bayesian evidence returns favoring a physically sensible, i.e. positive value of the sum of masses. Right. From the observational point of view, these DESI results indicate the need for a paradigm shift in our understanding of late-time cosmology. Yeah, I agree. Just going to drink some water. In the next section, I will argue that, from the point of view of fundamental theory, we should not have expected dark energy to be a remnant cosmological constant due to conceptual problems with the resulting cosmological model. In fact, I will argue that to describe dark energy, we need to go beyond the standard effective field theory treatment in which space-time evolves according to general relativity, that's our theory of the universe, and matter is described by an effective quantum field theory. There's going to be a lot to get into here, but don't worry, we'll get there. In the following, we consider a homogeneous, isotropic, and spatially flat universe described by this metric. So again, for people who are recent watchers, the metric, when we talk about a metric in space-time, what we're referring to is a way of measuring times or a way of measuring durations and distances. That's how we encode the geometric information, like curvature, of the universe. So when we say it's described by a metric, this is a mathematical description of roughly how curved the universe is and in what ways it's curved. So this ds squared, this is just kind of it's called the space-time interval. This coefficient of 1 in front of the dt squared means that time flows constantly at a fixed constant rate throughout the history of the universe. And this minus at squared, dx is kind of like, x is kind of like our spatial distance. This at squared says that the universe, the way that we measure distances in the universe gets bigger with time. A of t is the scale factor. If a of t gets bigger, the universe gets bigger. If a of t gets smaller, the universe gets smaller. In fact, it's going to describe it here. Where t is physical time, x are the co-moving spatial coordinates. Those are like the coordinates kind of pinned down at different places. And a of t is the scale factor. In the following, the Hubble length scale, L sub h of t, is the inverse of h of t, where h of t is the instantaneous expansion rate, will play a role. So you can imagine that the universe is expanding at a particular rate now. It's not expanding at a constant rate. It's expanding, at a certain rate, and it changes with time. And we've known that for a while. It was expanding more slowly in the past. It's expanding faster now. So this h of t just tells you how fast it's expanding now, or at a given time t. L of h is just the inverse of it, and it gives you a characteristic length scale. And the reason why it gives you a characteristic length scale is because h of t is measured in units of 1/seconds. And the reason why is because it tells you roughly a doubling time. So it tells you it doubles this much per second, or it increases its scale by this much per second. It's not like meters per second because we're talking about it doubling in size. So it has a doubling time of, it doubles once per 10 billion years. So that's why it's inverse time units. So if you take the inverse of that, you get something that has units of time. And because we're doing cosmology here, we just set the speed of light to 1. Typically, if you wanted to convert time to distance, you would take your time and divide it by the speed of light. But, sorry, that's not right. You would multiply it by the speed of light. And so that's all we're doing here. You get a length scale, which is roughly it's just a scale associated with the expansion rate of the universe. If the universe is expanding more slowly, then the length scale is bigger, means that you can roughly see more of the universe because the universe isn't expanding too quickly. If the expansion rate is very, very fast, then the length scale gets smaller because you can see less of the universe because it's expanding too fast. So this L sub h of t is going to tell you roughly about how far you can see in the universe. So, on length scales smaller than the Hubble radius, which is this Hubble length scale here, fluctuation modes simply oscillate. So think about just like a wave oscillating on a guitar string. It just oscillates because it's not too big. It's able to fit inside the universe. While on super Hubble scales, they freeze out and squeeze. So think about stretching a wave so much that one end can't talk to the other end because it's expanding too fast. Well, then it'll just freeze out at wherever it is. It'll freeze out. It'll kind of like solidify and not oscillate anymore. And so that's what's being talked about here. So while on the super Hubble scales, they freeze out and squeeze, leading to classicalization of initial quantum fluctuations. So initially you had some quantum fluctuations in the very early universe, and then the universe has expanded and froze out some of those oscillations that were particularly big because it was expanding too fast. And there's some nice, there's some references for some reviews on this kind of stuff, which is pretty standard cosmology. So what does this have to do with DESI? Well, we're going to talk about the Trans-Planckian censorship criterion and the DESI results. In the standard cosmological paradigm, spacetime obeys the Einstein field equations, and matter is considered to be a set of quantum fields. So the Einstein field equations is what's known as, these are the equations that describe general relativity. So this is relating curvature to matter. And the matter is considered to be a set of quantum fields. In the effective field theory framework, so this is a type of field theory, a type of quantum field theory. For those who are just joining us, the title of the paper is called Why the DESI Results Should Not Be a Surprise. Right, in the effective field theory framework, each such field, phi of x and t, is expanded in co-moving Fourier modes. So they're doing a Fourier transformation. So if you've taken, calculus, you know what a Fourier transformation. It's when you break things down into sines and cosines. And so this is just a way of expressing the field in terms of Fourier modes. Phi sub k of t is your Fourier mode, and then you can do an integral to get it back to your normal spatial modes. Right. So in the effective field theory framework, each such field, phi of x and t, is expanded in the co-moving Fourier modes, and each mode is quantized as a harmonic oscillator. So the way that we do quantum physics typically is, instead of working with the spatial fields, we work with the Fourier modes. There's good reasons for this. I'm not going to go into the details, but this is a pretty standard thing. And so you quantize each mode as a harmonic oscillator, basically like a spring oscillating back and forth. Right. At the level of linearized equations, meaning essentially the first order approximation, each Fourier mode evolves independently. So they just kind of do their own thing. They don't interact with each other. Gravitational and matter nonlinearities generate couplings between different modes. So once you start including gravity, and once you start allowing matter to self-interact, modes can now talk to each other, different modes, different. So by the way, you can think of modes as like different sine waves that are all kind of like overlaid on top of each other. So they can be oscillating. Typically, they kind of behave independently, but if you allow for interactions and you allow for gravity, then the different sine waves can talk to each other. In order to avoid, and this is the critical point of the paper, by the way, in order to avoid the Planck ultraviolet catastrophe, we need to impose an ultraviolet cutoff. No Fourier modes with physical wave number greater than some cutoff scale, expected to be either the Planck or the string scale, exist. Now I have to explain what's going on here. The Planck ultraviolet catastrophe is basically, if you do standard field theory, standard quantum field theory, and you just wait, let me back up. The way that we do standard quantum field theory is we basically take all of the possible oscillations, and you add them all up in some sense. You add them all up in some sense, and those will all contribute to a probability. And the probability is the thing you measure. The trouble is, there's an infinite number of possible oscillating frequencies, and so if you let the frequency diverge off to infinity, your answer will be nonsensical. You'll get infinity as a probability, and that doesn't make any sense. So what we do, that's the Planck ultraviolet catastrophe, by the way. Ultraviolet because it's high energy, and ultraviolet is what we usually call the high energy regime of a theory. Catastrophe because it's bad. So you impose an ultraviolet cutoff, i.e. a cutoff that kind of chops off your energy levels above a certain level. So you say you're allowed to add up all of the oscillations up to a certain point, and then chop it off, and nothing else beyond that contributes to it. This is pretty standard in effective field theory. And then it actually works. It might seem arbitrary, but it actually works. So you just kind of chop it off, and then you adjust the numbers, and then it works. It's magic, genuinely. And so the ultraviolet, the cutoff that's being implemented here is we say that there are no Fourier modes with physical wave number greater than some scale. So we basically restrict the value of k to be smaller than something. K tells you about the frequency. Tells you about the rate of oscillation, right? So, and you can place where you think that wave number will be. It's actually not quite k, but it's related to k. So you can put that wherever you want. You could put it at the Planck scale or some string scale or whatever. But you just put it at some really, really high energy where we can't measure. Now here's where the issue arises. Let's keep reading. In this setup, a unitarity problem arises. I'll explain what that means in a minute. In order to maintain the cutoff at a fixed physical scale, we have to continuously create modes. The Hilbert space of states becomes time-dependent. This is a serious problem for fundamental physics and is sometimes called the Trans-Planckian problem. So, the issue is that our universe is expanding, which means that the modes that are allowed can get bigger and bigger. And so, something is changing. Somehow you're just adding modes as time goes on. And that would mean that the set of all possible states is changing over time, which is like very clearly nonsense. And this is what's being referred to as the Trans-Planckian problem. If the universe were static, this wouldn't be an issue. But the universe isn't static. So we get this quote-unquote unitarity problem because the set of all possible states is changing. And that's really bad because like quantum field theory can't handle that. Which makes us think that actually maybe we're doing this wrong. Maybe, in fact, our universe doesn't allow for the set of all, or the space of all possible states to be changing, and so it will enforce some sort of behavior for the expansion of the universe that ensures that it never actually creates new physical states. Let's keep reading. Given an expanding universe, a necessary condition was proposed to ensure that physics we currently observe be at linear order, shielded from this unitarity problem. Wavelengths which have to be created after the initial time ti, i.e. which are Trans-Planckian before the initial time, should never be able to exit the Hubble radius and hence classicalize. So you shouldn't be able to stretch a Planckian. You shouldn't be able to stretch a small, very, 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 very high energy wave enough that it becomes classical, that it freezes out because it spreads out so much, like we mentioned earlier. So essentially, there's this proposal that whatever the physics of the universe is, we need to make sure that that doesn't happen, so that so that we can't observe it, because if we could observe it, that would be a bad thing. It would mean that our physics is broken. So this condition, the Trans-Planckian censorship criterion, TCC, can be written this way. So here's the equation for it, and I'll explain it in a minute. For all times t greater than ti, where L sub PL is the Planck length. So let me explain. So this is the Hubble radius. Remember, this is the length scale of the universe. That if a wave's wave number gets bigger than that, then it classicalizes. For those just joining us, by the way, the title is Why the DESI Results Should Not Be a Surprise. So, we need that if there are going to be Trans-Planckian waves, these are waves that are very, very high energy in the early universe, they can't classicalize, because otherwise we'd be able to measure them and detect them, and that would be real bad. So instead, we're just going to say that that wavelength, the expansion, the ratio by which those waves would have expanded by, which is this ratio, a of t divided by a sub ti, this is the ratio by which the universe has expanded by. Classicalize just means that it freezes out, that the waves kind of get stuck in their, stuck in their ways rather than continuously oscillating. So we're going to take that ratio and we're going to say that the Planck length, which is the scale at which it's the wave number, or really we're talking about wavelengths here. It's the wavelength. The wavelength of these very high energy oscillatory waves shouldn't have stretched by more than the size of the Hubble radius. So this is the stretching amount, this a of t divided by a of ti, and this is the initial size of the waves. So if we impose this criterion, well, then those waves will always stay safe. They'll be happily oscillating, but they will never freeze out. For more detailed justifications of the TCC, see this reference. Okay, we could take a look at that if we want to. Note that this equation 5 should be viewed as a necessary but not in itself sufficient condition for a cosmology which is viable from the point of view of fundamental theory. So what they're saying is that if we're doing fundamental physics, we definitely need this. We might need more, but we definitely need this. Now we're actually just going to study this condition and see what it tells us about dark energy. In a non-accelerating expanding cosmology, the Hubble radius grows faster than the scale factor, and hence the TCC is automatically satisfied. So if you didn't have dark energy at all, then the Hubble radius gets big rather quickly because the universe just isn't expanding very quickly. The Hubble radius tells you essentially how far you can see, and because the universe isn't expanding too quickly, you can see more and more. And so in fact, it grows faster than the left-hand side, so you'll be fine. This equation is satisfied because this thing is growing faster than this thing. Fine. In an accelerating universe, on the other hand, the TCC criterion is very constraining. Applied to inflationary cosmology, it implies that canonical inflationary models described in the framework of effective field theory are inconsistent. So canonical inflationary models are those where you have very, very fast, rapid inflation in the very early universe. And that would mean that you're breaking this inequality, which implies that they're inconsistent, unless the energy scale of inflation is very low, in which case it would take fine-tuning to obtain a sufficiently large amplitude of cosmological perturbations. I'd have to read the review on that. I'm not super familiar with what they're talking about here, how you can get away from that, but you know, there's a reference here if you want to look at it by Blammer, Laberlet, and Brandenberger. Right. The TCC has crucial implications for the dark energy mystery. If dark energy is a cosmological constant, then the Hubble radius converges to a constant which is approximately equal to h0 inverse at late times, where h0 is the present-day Hubble expansion rate. In this case, co-moving scales continuously exit the Hubble radius. After a time interval, delta t given by this, so this is h0 inverse times the log of the Planck length, times the log of the Hubble radius divided by the Planck length. So after this much time, scales which exit the Hubble radius will have been Trans-Planckian today and hence in the zone of ignorance. So this is saying if there's a Trans-Planckian oscillation today, like very, very small, after this much time, they will exit the Hubble radius, assuming that the universe has a cosmological constant, because the universe's expansion is accelerating. Essentially, you can just solve the field equations to get this result. What day do I do Ask a Physicist? It's Wednesday. Thus, if dark energy were a cosmological constant, the non-unitarity of the effective field theory would rear its ugly head after this time interval delta t, which is called the Trans-Planckian censorship time. To avoid this problem, accelerated expansion has to end, and hence dark energy has to be time independent. And there it is. That's the takeaway from this paper. Sorry, let me drink some water. Note that TCC, Trans-Planckian censorship constraint, is censorship criterion. Note that the TCC constrains all dark energy models in which accelerated expansion does not end at some point in the future. There are a couple of important remarks. Firstly, the TCC condition applies to any model which is based on effective field theory, and thus it applies to much more generally than only to string theory. On the other hand, if one were to construct a theory which is not based on effective field theory, then the TCC criterion would not necessarily apply. Recent efforts to, by the way, I should say, the way that we do quantum field theory today is with effective field theory. It's like the most effective way that we know how to do quantum physics. Recent efforts to obtain an accelerating cosmology using non-perturbative ingredients in string theory, obtain accelerating phases with time-dependent equations of state. So this is using non-perturbative string theory, you get time-dependent dark energy. Also, starting from a non-perturbative definition of superstring theory, the BFSS matrix model, one obtains an emergent spacetime and early universe cosmology which does not yield a cosmological constant. So this guy's saying that, you know, in string theory,
You don't get you get a time-dependent equation of state. In the context of superstring theory, there are other arguments which indicate that dark energy must be time-dependent. First of all, there are no-go theorems, which indicate that it is not possible to obtain a positive cosmological constant from string theory using standard effective field theory techniques. Secondly, string theory severely restricts the set of effective theory models which can be consistently derived from string theory. That's a typo. Most effective field theories which one can write down are in the swampland, leaving only small islands behind which form the string theory landscape. In particular, the swampland de Sitter conjecture sets a lower bound on the slope of the potential of a scalar field which might dominate the evolution of the late-time universe. In particular, this rules out dark energy being a cosmological constant, since this would correspond to a scalar field potential with zero slope. In fact, even quintessence models of dark energy are constrained by the DESI conjecture. So this whole section was talking about string theory, or the latter half of this section anyway. Because despite what you might hear on the internet, string theory is still like regarded as the best chance we have for a theory of everything. By the way. Like, it's still considered the best chance that we have. I don't know if I'm convinced, but lots of people are still studying it. So that's why there's all of this context with string theory. Right. All right, so let's read the discussion and then we're done. I have argued that from the point of view of fundamental theory, we should not be surprised that dark energy is time-dependent. At least in the context of effective field theory, a model with a bare cosmological constant as dark energy would be non-unitary. Formally, the argument is based on the TCC. The TCC, in turn, can also be argued for in analogy with Penrose's black hole cosmic censorship hypothesis. There's a lot of context there that I'm not going to unpack. Unfortunately, at this point, fundamental theory does not yet explain what dark energy is, only what it is not. That's a good one. It may be interesting to revisit scenarios of oscillating dark energies such as the ever-present lambda model, or the idea that an oscillating dark energy is a remnant of the screening of a bare cosmological constant via the back reaction of long wavelength cosmological perturbations. So this discussion section is just saying, look, there's good I have the hiccups. There's good justification for believing that dark energy is time-dependent, which is consistent with the recent DESI results. And we don't know what it is, but we do know, at least we have good reason to think, that it's not constant. So just a quick summary. I mean, it's a very, very short paper, only 2 pages. The acknowledgements are quite short, nothing to say here, and then a ton of references, which is, good science. So basically, the story of this paper is that we got this recent result from DESI, which seems to suggest, obviously it's not 100% confirmed, but it seems to suggest that the strength of dark energy is changing with time. It was stronger in the past, weaker in the future. And what this guy is claiming is that actually, this really shouldn't have been very surprising. Because if you let it be constant, at least according to this notion of the Trans-Planckian censorship criterion, then all of effective field theory just kind of breaks. And so we should, because effective field theory we reasonably expect shouldn't break, well then we need to make sure that our universe doesn't let it break, in which case the universe can't have a constant acceleration forever. So at least that's the justification here. I'm not sure how convinced I am, because who's to say that effective field theory has to work forever? But I think it's a really clever argument, and it's at least gives some credence to this idea that maybe DESI is actually right. So that is the end of the review today. We are going to call it there. Short stream, because it's a short paper. But I think it was a good paper. I actually quite liked it. And so I think I'm going to end the live stream here. And I will, if you missed the beginning, you can go watch it back on YouTube. It will be posted there right after the stream finishes. And I think we'll call it there. I'll see you guys tomorrow for Ask a Physicist. And remember, if you want to support me, there's ways to do that in the description in YouTube or in the link tree in my bio. You can join the Discord. You can like the live, all these lovely things. I'll see you guys next time.